Hello everyone, welcome back. Previously we mentioned about, we went through chapter 2 and in a brief recap, and we talked about the system, okay? The two different kind of system being the open and closed system. And we gave a few examples and basically three classes of open systems which are important to this module: boilers, condensers, pumps, turbines, and nozzles, diffusers. All right, and what is so important about these systems is we want to know the properties of the fluids when they run through these systems at the inlet and the outlet, so that we can evaluate the amount of work and heat done during the process. Okay, and the process is simply defined by the line that connects the two states, like how a line connects 2 points, okay, from one state to the next, from the inlet state to the outlet state, from the initial state to the final state. Okay, and the kinds of properties that we are going to look at. So chapter 3 is going to look at the idea, the fundamental principle of first law of thermodynamics. Okay, and that is where your heat and work will come in. Okay, heat is Q. Okay, for this time, instead of the volume flow rate when we were talking about fluid dynamics. So Q is heat, and heat energy is a form of energy, so the unit is joules. Okay, and work is W. Okay, and it is also a form of energy, so the SI unit is also joules. The first principle, right, the first law of thermodynamics is basically the conservation of energy. Okay, you remember during chapter 1 we talked about conservation of mass. Okay, we also know that there's this thing called conservation of momentum, which is in fact the force equation. Okay, force equilibrium equations. And when you talk about conservation of energy, then this is one of the cases. This is the first law. Okay, so the main equation is this: heat minus work is equals to change in the internal energy of the fluid. Okay, change meaning final U minus initial U, or outlet U minus inlet U. Okay, we will talk more about this later, but first we look at Q and W. So depending on what forms, whether it is a loss or a gain, whether it is an input or output, the sign will change. Okay, so for example, if the boiler provides 10 joules of heat to the water, okay, this is a heat gain by the fluid, by the system, so it will be a positive Q. Okay, but however, if your water is just left on the table and it loses heat to the surroundings, right? Let's say it loses 10 joules of heat, then this Q will be a negative Q. Okay, so this is a heat gain by the fluid, and heat loss by the fluid is negative. So for W, there is also a very similar comparison. So work is done when work is done by the fluid. Okay, in what kind of case is work done by the fluid? For example, you have a cylinder and piston, right? And the air inside, okay, is pushing the piston up because it gains heat or it gains energy, and it pushes the piston up. Okay, and because of this, your volume in the cylinder increases, right? So this is an expansion. So in fact, the air is actually doing work. So this is called work done by the fluid. So when work is done by the fluid, it is positive. So let's say it moves the piston up. Okay, and while it moves, it does a work of 10 joules. So work done by the fluid will be positive. Okay, now if you look at the reverse, initially at a high position, okay, the piston at a high position. Now instead of pushing up, right, I actually give a force to push it down. So my hand actually push the piston down. So the volume decreases. The air gets compressed. So this in fact is a work done on the fluid. Okay, the work is done on the air for this case. So this case, you will have a minus 10 joules of work. Okay, so the work done on the air is actually represented by a negative 10. Okay, so that is the idea. So it is actually shown here in the in the notes. Okay, and this here, equation 3.1, is your Q minus W equals to delta U. Okay, this for a start, this is the non-flow energy equation, meaning for closed system you use this equation. Okay, so for closed system you use this equation, but for open system, okay, this is a very generalized picture of any open system. It can be boilers, condensers, diffusers, anything. Okay, there will be an inlet, there will be an outlet, all right, and within the system something will be done. Okay, either work is produced or work is being input, either heat is gained or heat is lost, and whatever happens, by the time it goes out the outlet, it will be at a state 2, outlet 2. Okay, so at first look, right, if you look way below, okay, this is the steady flow energy equation. So for open system, instead of looking at Q minus W equals delta U, you're looking at a more complex equation over here. It may look very daunting, okay, because you have potential energy, kinetic energy, this thing called enthalpy, and you have a Q over here, which is the heat, and the other side is the outlet state, potential, kinetic, enthalpy at outlet, and then finally there is a W. But in fact, if you treat these first four terms, okay, as an equivalent of energy state at the inlet, and then you treat the, on the right hand side, the four terms as the energy state at the outlet, it actually becomes a very similar to the non-flow energy equations. So I'm just gonna go right here and look at the specific level of the SFEE. Okay, meaning that per kilogram. Okay, per kilogram, right? The equation 3.4 can be written. So at the inlet, okay, inlet, this is flow speed. C is flow speed, right? Plus Gz1. This is potential energy at the inlet. Plus H inlet plus Q is equals to half C outlet square plus Gz2 plus H2 plus W. Okay, so in fact, if this is an energy state at the inlet compared to the energy state at the outlet, we call this a E1 and E2, and you do a bit of shifting. So you shift W over here, you shift E over to the right hand side, it becomes Q minus W equals to delta E, which is quite similar to your closed system equation. Okay, so the idea is still the same. Work done and heat gain, the net effect is being accounted for into the change in the energy state, okay, between the outlet and the inlet. That is the idea. All right. So this equation is long, but there is always a way to simplify it even further by looking at what device, what open system are we actually looking at. Like I have mentioned previously, you have turbines and pumps, right? Boiler and condenser, and diffuser, nozzle. So with each type of device, there is certain assumptions that you can actually make. Okay. So let's say for pumps and turbines, okay, we can ignore the kinetic energy and potential energy. Okay, ignore. It doesn't mean that there isn't any. Okay, there are still KE and PE, but it's just that the changes between the inlet and outlet, right, of the KE and PE are not as significant as the other terms. Okay, so we can ignore. They will be very small compared to your H, your Q, and your W. Okay, and your pumps and turbines, we can also assume one more thing, that your Q is 0, meaning let's say it's an insulated system, no heat is lost, okay, or gained from the surrounding. So because of this, right, your original long statement, your original equation, okay, gets this cancelled, this cancelled, this cancelled, this cancelled, and this cancelled. You're only left with H1 equals to H2 plus the work done by the turbine. Okay, see, if this is a turbine, right, your W will be positive, then it will mean that your H2 is smaller than H1. But if it's a pump, the work done is actually on the fluid, this W is actually a negative value, then it will mean that your H2 will end up bigger than H1. Okay, just take some time to think about that. So, and then for boilers, condenser, you can also ignore KE and PE. Okay, but this time, boiler and condenser, right, the idea is just a transfer of heat between two fluids. Okay, so there is a transfer of heat, but there is actually no work done. Okay, there are no moving parts in the whole system, so you can treat work done as equals to 0. So in that case, right, your equation actually becomes this, simplified to become this. Okay, so this is for pumps and turbines, this is for boilers and condensers. Okay, and last class of system, your diffuser and nozzles. Okay, the primary function of this system is to speed up or slow down the flow. So actually you cannot ignore the kinetic energy. So you cannot ignore the kinetic energy changes. So you can only ignore potential energy. Okay, and because there's no moving parts, work is 0, and we can treat it as an insulated flow. Q is also 0. So at the end, you're only left with inlet KE, outlet KE. Okay, so the first law becomes simplified into this form for diffusers and nozzles. So this is the whole idea of chapter 3, okay, talking about the first law, conservation of energy, and depending on which system we're looking at, we can simplify into different kinds of different forms of the equation.